When you apply Lorentz contractions on a spacetime diagram, you see that the primed axes need to be shorter than the unprimed ones. How can this be? The primed axis is the hypotenuse of this right triangle. It should be the longer distance. In this video, we will dive into this wonky geometry of special relativity to answer this question and then have an epiphany in the process. All the pieces just fall into place once you switch to a geometrical viewpoint. Well, to start, we need to ask one of those annoying questions. What is a distance? Because it is such a trivial concept intuitively, it becomes extra hard to define it mathematically. Luckily, mathematicians have done it. What defines a distance in a mathematical space is a structure called the metric. Very roughly speaking, you can think of the metric we usually use as the Pythagorean theorem. Using it, we sum the squares of two perpendicular distances that we choose to get what we can call an absolute distance. I will explain what I mean by that in a second, but this theorem is precisely why we think the primed axis should have the longer length, right? Well, it turns out in spacetime we use a different metric. It actually works by subtracting the time axis distances from the space axis distances. So s squared, what we can call a spacetime interval, is defined as x squared minus c squared t squared. This definition shows that the closer a line gets to the line of a light beam on a spacetime diagram, which is always at a 45-degree angle, the shorter the intervals get on that line. Even though when you draw it, visually the line looks longer on the diagram. Just as a teaser for later, there must surely be a way for us to find points on all of these lines that represent the same distance from the origin. It should appear that the points land further and further on the lines as we get closer to the light beam because the lines get shorter and shorter. So let's just keep that in the back of our minds. And in the meantime, let's dive into this concept of a metric. In this part, I am going to talk about some simple things that we all already know really well, but we are only doing this to generalize these concepts into a deep and profound geometric viewpoint, which we can then use to master special relativity and also pave the way to general relativity. So if that sounds like a good deal, let's get after it. First of all, let's clarify this confusing language we have been using. I mean, the metric defines a distance, but it tells us to add the squares of two distances in the process of defining what a distance is. Well, what I've vaguely called an absolute distance is really what the metric defines. The other two distances we've added have no geometric significance because they require a choice of coordinate axes. For example, let's say that you go outside and observe a bird fly from one tree to another at a perfectly straight line, to keep things simple. If you measure the length of this line by just putting some meter sticks between the trees, that is an absolute distance. But if you instead choose to be impractical about it and pick two coordinate axes to split this distance up and say that, okay, the bird flies this much in the x direction and this much in the y direction, and then you add the squares of these distances, you still get the same distance as you would have measured with the meter sticks. But there is ambiguity here, right? You can just as easily choose your coordinate axes to be tilted a little bit this way, and you would measure a shorter x distance and a longer y distance so that the squares still add up to the same absolute distance. Now, you would have encountered this before in any math or physics courses that use vectors. You can write down a vector in components as defined by your x and y axes and their unit vectors. Then you can rotate your coordinate axes and even change the lengths of their unit vectors to write the vector in new components. But none of this actually affects the actual length of the vector. What we can do is take a dot product of the vector with itself to get this absolute length. This is how we define the square of a vector. And then we can carry the dot product out with the vector components that we wrote down. But then of course it has to be the same for the other components, as that is still the square of the same vector. So these two dot products have to be equal to each other, and that is how we can kind of compare the lengths of the different unit vectors from the different coordinate axes. So the dot product is another way to get to absolute distances. And as you might guess, the dot products on a vector space are also defined by the metric of the space that they live on. And it is the same thing as applying the Pythagorean theorem. When we define the square of a vector through its dot product by itself, we're still just adding the squares of the components, right? So the vector is what we call a geometrical object. It's as if it lives beyond the reach of our algebraic tools. The coordinates and the axes we use to represent the vector are just labels. What the metric and the Pythagorean theorem can do then becomes something pretty dang powerful. They allow us to reach these geometrical objects that live beyond our algebra by using our algebra. And they get rid of that ambiguity, because quite remarkably they work for any coordinate axes that we choose to use, even though we have an infinite number of choices. So how about coordinates in relativity? On a spacetime diagram, we already have two sets of coordinate axes. Did we choose these coordinates? Not quite, right? The observers chose them. The coordinate axes in relativity come included in the package with the observers and their corresponding inertial reference frames. So, mathematically speaking, Alice, Bob, Charlie, Denise, no matter the origin or personalities of these observers, the fact is, they are nothing more than a choice of coordinates. That's all they are, and it's still really difficult to get them to agree on something, right? Luckily, now we have the metric, and with it, we can compute some sort of interval in spacetime that will be agreed upon by all observers, as it must be invariant through a change of coordinates. These objects are called Lorentz invariant because they are invariant through Lorentz transformations. Let's start by first seeing that this absolute interval we have gotten from the metric is indeed Lorentz invariant. This is something you should do at least once in your life, and I'd recommend you do it yourself. I'll just quickly go through it so we are all on the same page. So we are claiming that these s-squared intervals are the same for both coordinate systems, and we have our Lorentz transformations to switch between the two. By the way, if there is anything that doesn't look familiar to you about these spacetime diagrams and transformations, be sure to watch the last video where we discuss and derive it all. So all we are doing here is taking these Lorentz transformations and squaring them so that we can place them into this s-squared equation. We can then factor out the gammas that come from both of the terms. And at the moment it does look like a little bit of a mess, but we can first have stuff cancelling out right here. We can see that xvt terms are going to cancel. So down here we can go ahead and collect the x squared terms and the t squared terms together. And stuff is now resembling the factor gamma squared. What we can do for the t squared part is to divide everything by minus c squared, so that on the outside we get minus c squared t squared as we want, and on the inside we just happen to get another one of these 1 minus v squared c squared terms. Now by writing gamma for what it is, which is 1 over the square root of 1 minus v squared over c squared, that means gamma squared is going to cancel these orange terms inside the parentheses. So in the end, everything does magically end up cancelling out, and we do get that the intervals are equal to each other. Always lovely to see that happen. And that means that no matter what coordinates our observers assign to whatever points, they will always agree on what the s-squared interval is. It's a geometrical object, so it lives beyond the pesky coordinates of these observers. Well, finally, when I first saw that such a thing exists in relativity, it was really comforting because it's so difficult to orient yourself. We only have rays of light that people agree on, and well, those are fast and they're counterintuitive. Now we have intervals that everybody agrees on. So what we actually can do now is just think of spacetime as a diagram and the observers as just coordinate axes on top of it. Later down the series, we are going to fully switch to this geometrical viewpoint and use tensors and 4 vectors to do relativity purely geometrically, which will also create a relatively seamless transition into general relativity. For now, we are going to place these invariant intervals onto our spacetime diagrams to see some really cool behavior. So let's go back to our old geometry to keep building our intuition through contrasting. So on our regular XY diagrams, if we were to put all possible points that are the same invariant distance to the origin onto a plot, what would it look like? Wow, it's a circle. As we go around this circle, we see the same relation of x squared increasing as y squared is decreasing as in the rotation of the axes, right? So it's as if the shape of the invariant points when you put all of them on a plot gives you the shape of your transformation. This is a rotation, so it leaves all the lengths the same and it gets you back to the same point if you rotate enough, and it doesn't really matter much which direction you rotate towards either. You can span all of the points on the circle in either direction. Furthermore, any coordinate axes that you draw on this plot will inevitably intersect this circle at a distance r from the origin. I know our trivialness meter is going crazy as I speak, but now let's try to get the analog of this onto a spacetime diagram where things will get interesting again. So x squared plus y squared equals r squared happens to be the equation of a circle. And what is x squared minus t squared an equation of? This is a hyperbola, right? Those conic sections from calculus might finally come in handy, maybe. Just as with the circle, we have an infinite set of points that all represent the same distance from the origin. And just as with the circle, all of the lines that we draw from the origin, so that is all of the coordinate axes, are going to intersect this hyperbola at the same distance from the origin. Aha, so remember that teaser question I've teased before? This is how we identify those points of equal distance from the origin. They are all on this hyperbola. So surely this is all we need to get the relationship between the coordinate axes, right? We know where they actually represent the same distance from the origin. So the shape of spacetime is now starting to shape up here. Just like how these circles represent all the sets of points of different distances from the origin for two-dimensional space, the hyperbolae do the same for spacetime. They are the wavefronts, the equipotential lines for spacetime. It is woven through with these hyperbolae. And the best part? This is absolute. All observers agree that spacetime diagrams look like this. They just place each other's coordinate axes at different angles through it. Now also by drawing a few of these lines, we can see how the Lorentz transformations differ from rotations. They have more of a scissorsing effect, right? The x-axis rotates upwards as usual, but the time axis, due to that minus sign on the metric, actually rotates downwards. And both of the axes get closer and closer to the light beam in the middle. So the rotations in two dimensions eventually loop back to where they have started, hence the circular shape of the invariant points. The Lorentz transformations just asymptotically get closer to the x equals ct line. There is no end to it, hence the hyperbolic shape of the invariant points. This also means that there is a kind of orientation with the spacetime diagram, right? With the rotations, you can always rotate to get your y-axis to be your x-axis. With the Lorentz transformation, your x-axis just gets closer and closer to a light beam, and it will never switch places with the time axis. We'll get back to this in a second to define those timelike and spacelike intervals, but first let's go ahead and actually derive the Lorentz contractions using our new metric. So, all around both of our axes we have these hyperbolae, and the time side has an equation for minus s squared. The space side has plus s squared. Spoiler alert, this is what orients space and time. So down here we have these 2 points, let's call them P and Q, where the time axes of 2 observers are intersecting the hyperbola. We know that both of these points are the same distance from the origin. What we want is a transformation between the 2 coordinates. So The point Q has coordinates 0 and t prime q for the primed observer, and then xq and tq for the unprimed observer. Well, both sets of coordinates are on the same hyperbola, so we can go ahead and write down the minus s squared equation and set them equal to each other. For the primed observer, we have x prime q squared, which is going to be 0, minus c squared tq prime squared. This is equal to xq squared minus c squared tq squared. Well, let's go ahead and divide everything by minus c squared. That worked last time, so we get t prime q squared is equal to tq squared minus xq squared over c squared. Now there is another thing that we can use here. This t prime axis, where x prime is equal to 0, the unprimed observer is always going to see this as x equals vt. Well, this is just another way to write that v is equal to x over t, right? And this velocity is measured between the two observers, so it has to be agreed upon. So if we go ahead and plug in that xq squared is equal to v squared tq squared, we'll be able to factor the tq squareds and already see that gamma squared emerge right in that parenthesis again. So in the end, in just a few lines of algebra, we get that tq prime is equal to tq over square root 1 minus v squared over c squared. So tq prime is equal to gamma tq. Well, that's time dilation. Right there, it takes you like 3 lines of math to derive it using the invariant interval. And of course, you can do this for length contraction. You just have to use the fact that on this x prime axis, t equals v over c squared x has to be true. Again, if this looks unfamiliar, be sure to watch the spacetime diagrams video where we derive all of this. So, back to that orientation business. What gives the space and time orientation to spacetime is that minus sign of the interval. If you're on the timelike side of the axis, then the s squared has to be negative. If you're on the spacelike side, it has to be positive. So say we have a point right here on the t-axis. That means x is equal to 0 here, and so s squared is just equal to c squared t squared. Similarly, we have x prime equals 0, then c squared t prime squared is equal to s squared. So if you have a point on the timelike side of the diagram, there always exists a line that you can draw such that the line is the time axis of a certain observer, right? You can always have this point represent a time interval from the origin. Now, if this s squared is smaller than 0, it means that the c squared t squared is equal to a negative number. Does that mean that these time coordinates are actually imaginary? Well, no, this used to be an old convention, but it is now replaced by the geometric viewpoint, which simply says that the minus sign for time is induced by the metric. It comes from that minus c squared t squared on the metric. So when we write intervals up here, even though c squared t squared is equal to s squared, it is better notation to just keep the minuses there, as this is what indicates that this is a time interval. And similarly, you don't have the minus signs when you write a spacelike interval, so that you know which part of the metric you're actually working with. Now physically, any curve that we draw on the timelike side of the spacetime diagram, and by the way, these curves on spacetime diagrams are called worldlines, the timelike worldlines can be followed by anything that has mass. That means they are traveling slower than the speed of light. Therefore, we have to be careful when we're drawing the worldlines because at no point can they have a slope that is more horizontal than a light beam. If there is a worldline that is more horizontal than a light beam, say the worldline between these 2 points here, there can be no interactions between these 2 points. They are just separated in space, which is what we call a spacelike worldline. As for everything that has no mass, they move along with light on this x equals ct line, which is called a null or light-like worldline. Now, for any point on the spacetime diagram, we define a past and a future using these x equals ct lines. These are called light cones. Well, they are cones in 3 dimensions. Right now it's just a light x. But the light cones in your future kind of define everything you can possibly interact with, as anything outside the light cone would have to travel faster than light to get to you. The light cones under the point represent everything that could have interacted with you just up to this point. That means that your past light cone expands as you move up in your time axis, because now there is more time for light from more distant places to reach you. But up to this point, all the stars that you can see in the night sky are contained in your past light cone. And anything that lies outside these light cones are simply unreachable. Well, let's see another example with 2 points this time. So say we have these points P and Q that are timelike separated. So Q is in the future of P. If we draw the light cones for these 2 points, we see that they put many regions on the spacetime diagram. This gray area here is the past for Q and the future for P, well, which is natural because Q is in the future of P, but we also see some points that are unreachable for P and unreachable for Q. So what's interesting here is that P can actually evolve in spacetime to become Q, right? Well, since we have independent regions that are unreachable for both Q and P respectively, it means that as P evolves into Q, some of the regions that used to be reachable now become unreachable. How about 2 points that are spacelike separated? Well, if we draw the light cones for these two, we have a first intersection up here, which is where anyone on the spacetime diagram can first possibly interact with both of these points at once, right? Say that P and Q both emit light beams in opposite directions, there can be somebody standing in this orange point to see both of them. Or if they were to both start traveling close to the speed of light towards each other, this is more or less where they would meet. Now, the region that is enclosed between them is the uninteractable region for both of them. And around it, we have the uninteractable regions for P and Q respectively. But this time, since they are space-like separated, P can never evolve into Q. The blue region is the common region where they can both get information from and can interact with or could have interacted with. So, later in the series, once we actually switch fully to the geometrical viewpoint, everything that we have done here on the spacetime diagrams is going to come in handy to give us the intuition that we need. If you found this video helpful, maybe share it with a friend that can also find it helpful. And stay tuned for the rest of the Special Relativity series.